this segment, we're going to look at graphing rational functions. And specifically, the example I'm going to do here is to graph a rational function that has a slant asymptote. I also have other videos where I'll graph rational functions with other things happening with them. Maybe they'll have a point on the horizontal asymptote that they cross, or a hole in the graph, or maybe it's just a regular graph where it just has its vertical asymptotes, horizontal asymptotes with no points that are crossed, and that sort of thing. But I have several different videos that go along with different scenarios for graphing the rational functions and their graphs. So I invite you to look at those videos. I have them linked in the description. So for our example, now, a rational function is a function that is a polynomial divided by a polynomial, or a function that can be written as a polynomial divided by a polynomial. Now, if you remember, polynomials are algebraic expression in which the exponents on the variables are whole numbers. And whole numbers are numbers like 0, 1, 2, 3, 4, 5, etc. So all my exponents on my letters in the numerator and denominator are going to be exponents that are whole numbers, and have a polynomial on the top and a polynomial in the bottom. When you have that, it's called a rational function. Now, the thing about knowing that it's a rational function when you start is that you have an idea then of what information you want to gather before actually going to draw the graph. And with the rational function, the information we want to gather is first the Y-intercept, and to find the Y-intercept of any curve of anything is we set x equal to 0. So if our graph actually has a Y-intercept, we'll find it that way. Now, the second thing you want to find are the x-intercepts. And you find x-intercepts by setting y equal to 0. Next up, you want to find out whether you have vertical asymptotes or possibly a hole in the graph. So that'll be our step 3, is look for vertical asymptotes. Or if we possibly have holes in the graph. The vertical asymptotes will happen where we have x values that make the denominator of the function 0, but it does not make the numerator 0. So for vertical asymptotes, this is a non-zero number divided by 0. So the x values where that occurs, that's where we'll have a vertical asymptote. Holes in the graph are a little bit trickier. First, if we have a value of x that makes the denominator 0 and the numerator 0, that means there's something going on there and we have to investigate it further. I'm not guaranteed that it's a hole in the graph. What I have to do is, if I have a value of x that makes the denominator 0 and also the numerator 0, then x minus that number is a factor of both the denominator and the numerator. And when I remove that common factor pair, I look and see what happens at that value of x again. If after removing that common factor pair, I get a non-zero over a non-zero, then I'm going to have just a hole in the graph at that x value. If after I remove that common factor pair, I get 0 in the denominator with a non-zero number in the numerator, then I would be back to having the vertical asymptotes. So I have to be careful with 0 over 0, 0 in the denominator as well as the numerator, and after simplification, I have non-zero over non-zero. That's when I would have a hole in the graph at that x value. So basically you actually just have the graph and you take your eraser and you erase out a little bit at that x value, comma, whatever that y value is, you erase it out and you just make an open circle there. So those are things that we have to look at in step 3. The hole in the graph one, that would be for another video. Now 4 is to find your horizontal or slant asymptotes. And then when I'm looking at if I have horizontal or slant asymptotes, I also want to see if the function crosses the horizontal or slant asymptote. So your curve will never cross a vertical asymptote, but it might cross a horizontal or slant asymptote. Your horizontal and slant asymptotes are actually your end behavior of this graph, what the trend is of the y's as you look forever left or forever right. And then our 5th step is to just get some ordered pairs, some well-chosen values of x, run through the function and get the y out, to be able to see then what we need to do to graph the function. So we're going to generate some ordered pairs. And graph it. And you may be thinking in the back of your mind, why am I doing all this when I can just put it through a graphing calculator and see the picture? Well, there's some stuff that your graphing calculator is not going to tell you. There's actually some rational functions where your graphing calculator shows you something entirely different than what the actual graph is. So when you get and gather all of this information ahead of time about your rational function and then set up the skeleton of all of these pieces, that makes you much better at setting up your graphing calculator's window, your table function, and to be able to get much more accurate of a graph of your rational function than if you just tried to rough-hand it off of the picture that the graphing calculator is giving you. Case in point is the holes in the graph. You know, it's just going to blow right through them. You wouldn't even know to show that on your graph if you didn't do the work ahead of time on paper. Now, this kind of outline of gathering information when you're graphing a rational function is the set of information you want to go gather every time you're asked to graph a rational function. So as soon as you see that it's a polynomial divided by a polynomial, or if it had separate terms with a fraction at the end, you got common denominator and could write it as a polynomial divided by a polynomial, these are the things you gather before you then go and graph. So let's gather them all from this particular example. Now remember, f of x is just another name for y. So I want to think of that as y equals, and I'm going to take out the x's, and I'm going to put zeros in instead. So my y-intercept is y equal 0 squared minus 0 minus 12 over 0 minus 2. Well, 0 squared is 0, and 0 subtract 12 is negative 12. 0 subtract 2 is negative 2. And overall, negative 12 divided by negative 2 is positive 6. So I have the ordered pair 0 in for x and 6 came out for y. I have an ordered pair 0, 6 that I know my graph goes through. Next up, the x-intercepts. I set y equal to 0. So I go back to the original function. Again, f of x is just another name for y. So I write this as 0 is equal to x squared minus x minus 12 over x minus 2. Now, this is a fraction, and a fraction, a division, will only come out to be a 0 answer if I have 0 in the numerator and I don't have 0 in the denominator. So what I want to do is find the values of x that make the numerator 0, and then I double check that they don't make the denominator 0. And the x's that make the numerator 0 but not the denominator are the x-coordinate of my x-intercepts. So we're going to take this x squared minus x minus 12 equals 0. factor it. That's x minus 4, x plus 3 equals 0. Set each factor equal to 0 and solve. X minus 4 equals 0. Add 4 to both sides. X equals 4. So I have 4 comma goes in for the x. 0 comes out for the y. And then x plus 3 equals 0. Subtract the 3 from both sides. X equals negative 3. So when x is negative 3, 0 comes out for y. So I have those ordered pairs. Now, what about vertical asymptotes or holes in the graph? They both have it where we're talking about situations and the values of x that make the denominator 0. So here, I'm going to take and focus my attention on the denominator. X minus 2 equals 0. Add 2 to both sides, x equals 2. And I check, if I put 2 through the numerator, 2 squared is 4, minus 2 is 2, minus 12 is negative 10, not 0. So I have a non-zero number in the numerator and a 0 in the denominator. So my x equal 2 is a vertical asymptote. So keep that information. And then next, horizontal or slant asymptotes. Now here's the thing. I will have a slant asymptote with my graph if I don't have a common factor pair that removes this down to where I don't have a quotient anymore. And the numerator power is 1 bigger than the denominator power. So the degree of the numerator is the same as the highest degree term. So the degree of the first term is 2, the degree of the second term is 1, and the degree of the third term in the numerator is 0 because there's no factor of x there. So the biggest degree I ever said, 2, 1, and 0, is 2. So my numerator degree is 2. My denominator degree is the first term of the denominator's degree is 1. The second term of the denominator's degree is 0. So the biggest degree I said was 1. And 2 is 1 degree bigger than 1. So I will have a slant asymptote. And also, I saw that fraction does not simplify to a non-rational expression. So how do I find the slant asymptote? There's a couple different ways to do it, but the way we are going to do it, or I'm going to show you in this video, is to do long division of the polynomials. So if you need to review long division of polynomials, I've also put a link to the video on a long division of polynomials in the description of this video as well, so that you could click on that and just kind of get a quick review. Well, with long division of polynomials, we're going to divide the numerator by the denominator. So I'm going to take my division, and the numerator is in the division box, and I'm dividing by the denominator. Now when we divide this, you make sure that you're in descending order for both what you're dividing into and what you're dividing by. If you had skipped any terms, if there wasn't an x to the first term or something like that, you would need to move it over and leave a spot for it. And then you take first term of what you're dividing into divided by first term of what you're dividing by. So x squared divided by x is x. Multiply that x through the divisor. So x times x is x squared. X times negative 2 is minus 2x. And then you subtract. And to subtract, you want to change the signs and then combine like terms. So we're going to change the signs and combine. X squared combined with negative x squared is 0. Negative x plus 2x is a positive x, and bring down the minus 12. And then do it again. The first term of what you're dividing into, x, divided by the first term of what you're dividing by, x. Well, x divided by x is 1. So I write plus 1. 1 times x is x. 1 times negative 2 is a minus 2. Then I subtract. So I change the signs and combine. X combined with negative x is no x's, they cancel out. And then negative 12 plus 2 is a negative 10. And now this degree, negative 10, is smaller than the degree of what I'm dividing by, so my division is done. And y equal the quotient is your asymptote. And in this situation, my asymptote has an x term as well as a constant term, so it's actually going to be a line that has a pitch to it. When you are working a problem and you do that division in that step with a rational function and your quotient is just a number, y equal a number is a horizontal asymptote. So horizontal, or does it have a pitch with it? Is it slanted? Okay, so that's our asymptote. And then when your remainder is just a number, it doesn't have a letter in it, then that's telling you your graph is not going to have a point on that slant asymptote. So now what we want to do is to just look at putting that information down on a grid and then going through for our 5th step and getting some table of values. What I've done is just kind of condensed our information, made our table of values that you could get either off the graphing calculator from your table function or just run some values through. And we're going to plot each of these. So we're going to plot the points for the function itself in black and draw the asymptotes in like a pink color, so they're contrasting colors. So my y-intercept, so 0 went in for x, 6 came out for y, so don't go left or right, go up 6 and draw the dot. 1, 2, 3, 4, 5, 6. There's your y-intercept. Next, your x-intercepts. Here we have an x-intercept of 4, 0, so go right 1, 2, 3, 4, don't go up or down. And my value of negative 3, 0, so go left 3, don't go up or down. And it's really important to use correct notation here, so you're making good information for yourself, so you don't get confused when you go to graph it. So intercepts you want to write as ordered pairs, and asymptotes you want to write as equations of lines. So when I got my x equal 4 with my x-intercepts, I got x equal 4 because I put 0 in for y. So it's the ordered pair, 4 for x, 0 for y. And then I also got x equal negative 3 for my x when I put 0 in for y. So I have another x-intercept of negative 3 for my x, 0 out for my y. So make sure that you record it correctly. Now next up, we have a vertical asymptote of x equal 2. So since it's a vertical asymptote, we'll go to x equal 1, 2 and draw in our dashed vertical line there. So there's your vertical asymptote at x equal 2. And then we have our horizontal or slant asymptote. We ended up with a slant asymptote of y equal x plus 1. Now, y equal x plus 1, this is just a line, but it's an asymptote. So you want to graph it in a different color so you don't get confused that the points are actually on the curve, that you realize the points are actually helping you set up to get the asymptotes part of the picture. So you can get, and for an equation of a line, the correct graph of it by plotting a couple points. So if x is 0, for example, 0 plus 1 is 1. So 0, 1 is a point on my slant asymptote. And that's, let's say, x equals 3. Well, 3 plus 1 is 4. When x is 3, 1, 2, 3, my y value is 4, 1, 2, 3, 4 on my asymptote. So you want to make sure that you mark it that it's an asymptote. Okay, and now it's just a line. So we're going to connect these dots to make our slant asymptote y equal x plus 1. And again, remember we got that because our degree of our numerator was 1 bigger than our degree of our denominator, and I didn't have where the fraction would simplify down to something that wasn't a rational expression with it. It didn't have a common factor of x minus 2 top and bottom. All right, now let's look at what we have so far. So just kind of as an overall view, I only have this one vertical asymptote. So I've graphed to the left of the vertical asymptote. If I had more than one between each pair of vertical asymptotes, and right of the rightmost vertical asymptote. So I want to figure out, like, to the left of the vertical asymptote, where's my graph? Well, my graph is going to either be down underneath the slant asymptote or up above it. Because it's a function, it has to pass the vertical line test. So it's either going to be below or above it. And I also see these couple points that I got from doing the structure information from the beginning. So I know it has to be up above the slant asymptote when I'm left of the vertical asymptote. And I see that an x value of -3 is the smallest x value I had in my information from the structure part at the beginning. So I would want to plug in x values that were just left of -3, like -4, -5, just to make sure I get some verification that that's right. So if I plug in x equal -5, it ends up that your y comes out to be -2.57-ish. So x equal -1, 2, 3, 4, 5. I get -1, 2.5-ish, so kind of about here. When x is -4, I'm at like -1.3. When x is -3, I've got a verification that my y is 0. When x is -2, left 2, I go up 1.5. I'll let you see it there. 0, 6 is what I had for y-intercept. 1, 12 is up off my graph. So I can see that the trend is like this, and it would continually get closer and closer and closer to that vertical asymptote on that left-hand side, but it would never touch it. Okay, then what about to the right of that vertical asymptote? Well, it's either going to be underneath the slant asymptote or above it, kind of a loop there. But I have a point from the information that we gathered that is within this region below the slant asymptote. And my ordered pairs verify that. When x is 3, y is -6. So write 1, 2, 3 down 6. And again, I just took out all the x's, put in 3, simplified this, and it came out to be -6. When x is 4, I get a y value of 0, which verifies I put it into my calculator right. When x equals 6, I get 4.5. So 1, 2, 3, 4, 5, 6, and then up 1, 2, 3, 4.5-ish, like there. So we get in this one that the graph looks like that on that side of it. So here, you can almost imagine that if you had a horizontal asymptote, curve would be up here and down here. But as it tilted, this part fell and that part opened up. And for this particular equation, the regions that had the graph were here and here. In a totally different rational function where my degree of my numerator is 1 bigger than the degree of the denominator, it's possible that instead of having the graph up there, I would have it loop down here and loop up there. It just depends on the specifics of your problem. But you would find that out from getting your information in your outline and then getting some y values for some key points. And the other thing I want to mention is that sometimes when it's in these parts where it's looping around below or above, they may be way outside of your window if you didn't know in your table function to look at y's that were way beyond what your window was. So let's say your y's were like in the 20s and the 30s. you need to make sure your window goes a Y max that would catch that. Or maybe they were negative. You'd need a Y min that would catch that so you could see the overall picture. So that's why it's really important to get this outline information whenever you're graphing a rational function and use that to get some key components of your rational function, and then get the specifics to connect the points with your table in your fifth step.